this chapter of the book is on the definite integral, which is a continuous sum of infinitesimal contributions, whatever that means. I mean, part of our goal is to define what that means, or what it should mean, what we'd all agree, hopefully all agree that it means. The first section is just, this first section of the chapter is just on some basic notation and properties of summations and also differences. So this may seem a little basic, a little not like calculus, but we need this for all the rest of the stuff that we'll do in developing the definite integral, and later we'll need it for infinite series. So sums and differences. So first, it will be convenient to have a notation for an interval of integers. So I'm going to use m and then dot dot n, where these are integers. This will be the set of integers between m and n, including m and n. Set of integers between, and between is kind of ambiguous. I mean, including m and n. So I'll call this an integer interval. You know, a trivial example, 3 dot dot 7 means the set 3, 4, 5, 6, 7. Technically, I mean, it's an ordered set, but the size of the numbers, the less than, already puts an ordering on them, so it's not so important to distinguish in the notation between an ordered set and just a set. It's a set of integers between m and n. I also mean to allow for m and n to be positive or negative infinity, so that you could go, so that negative infinity n, dot dot n, would just be a set of integers, so less than or equal to n. And if I put m dot dot infinity, that's the set of integers greater than or equal to m. And if I go from minus infinity to infinity, I mean all the integers. So I'm just allowing m and n here to be plus or minus infinity. Okay. You should have seen, if in differential calculus, you should have seen sigma notation. Sigma notation for summations. So something like, this is a capital sigma, and you write things like this. So what does this mean? It means you read the sigma as summation, and you read this as the summation as k goes from 3 to 6 of k squared. What does this mean? It means first you plug in 3 for k, and you get 3 squared. And the sigma says add to that. What you get when you plug in k is 4. You're going to let k go from 3 to 6 by 1 each time. So when k is 4, you take 4 squared, and you add that, and then you let k be 5, and so you add 5 squared, and you let k be 6, and you add 6 squared. This is sigma notation for summations. It's more generally, you write the sum as k goes from m to n of f of k, where f is some function of k that includes the integer interval, whose domain includes the integer interval from m to n. In this context of summations, we frequently subscript by the k. Instead of writing f of k, we write f sub k. This is very standard, and I'll use this all the time. The k here is called the index of summation. K. It is, it's what's known as a dummy variable. It's called that because it really doesn't matter what you call it. If you replaced, so does the k here matter? No. Well, I mean, it matters, but does it matter that it's called k? No. If I replace the k by a j here and a j here, that doesn't change the summation. It doesn't change what it is because it still means, okay, now you let j be 3 and then put j is 3 into here, and so you get 3 squared. Then you let j be 4 and you get 4 squared. And you let j be 5 and you get 5 squared. You let j be 6, you get 6 squared, and the sigma still says add them together. So it doesn't matter whether the index is j or k or anything else that doesn't appear elsewhere in the problem. It's a dummy variable. We can call it anything we want. All right. Basic properties of summations. Well, there are a bunch of them. So basic properties of summations. These properties are all, the ones I'm going to write, are all obvious if you write out the terms and write plus dot dot dot. We're trying to get used to them in the sigma notation form where it looks more formal and where we can manipulate bigger sums without writing dot dot dots, and it will actually make a lot of our calculations later much easier if we have these properties explicitly laid out. So one of them, let me return to that example. J equals 3 to 6 of j squared. Okay, yeah, as we said, this is 3 squared plus 4 squared plus 5 squared plus 6 squared. But I could group that like this and like this if I wanted. And then, well, this is a summation. This 3 squared plus 4 squared I can think of as one summation, and 5 squared plus 6 squared I can think of as another summation. So this part in the parentheses is the sum as j goes from 3 to 4 of j squared. And then I add to that the sum as j goes from 5 to 6 of j squared. And clearly those are equal. What's the basic property? That you can split summations. Different people might call this property different things. But splitting summations, it's that if you sum as j goes from, or k, I guess I'll stick with k when I write the general properties. If you sum as k goes from m to some other integer p of some function f sub k that's defined in this integer range, then you could first take the sum as k goes from m to n of fk, and then pick up the summation there, and then go get the rest of it as k goes from n plus 1 to p. Here I would need that m, yes, and I should have said that before. Here I was assuming m was less than or equal to n. Here I would need m is less than or equal to n, and I would need n plus 1 is less than or equal to p, so this would need to be strictly less than p. And you can split up summations this way. So that's obvious when you write it out, and all you're doing is taking part of the sum and grouping this other part of the sum. But yeah, it's helpful to know this in this notation, that you can just stop any place in between m and p, some n value, and then just pick up the rest of the things. All right, what else what's another basic property? Well, another basic property is that we can shift indices. So shifting indices So again, let's just keep picking on this same example. The sum is j equals 3 to 6 of j squared. Okay, it's still what it has been the whole time, 3 squared plus 4 squared plus 5 squared plus 6 squared. If I want to, I can write this in a bizarre way. Seemingly bizarre, but there will be a point. I can say, add 5 and subtract 5 from each entry. So I can write 3 as 8 minus 5 squared. And then I can write 4 as 9 minus 5 squared. I can write 5 as 10 minus 5 squared. And I can write 6 as 11 minus 5 squared. All right, so these are clearly equal because this is 3, 4, 5, 6, and I've got them all squared. Why would you do that? Well, if you write this in terms of a summation now, you could write it as the sum as j goes from 8 up to 11. Sum as j goes from 8 to 11 of j minus 5 squared, which looks very different from what we started with, but all we've done is shift the index so that when j is 3, we get 3 squared. Here, when j is 8, we get 3 squared. We've just shifted things. And the general property is that the sum, I'll use a k for the index again, that if you have a function and a summation as k goes from m to n, then instead, if p is some integer, you can go from, let k go from m plus p to n plus p, and you want your function to start at the same place. This one, when the initial value is f sub m, that's what we need here too, so we have to subtract p, the k minus p. This is what we're seeing in this example. In more normal functional notation, it might look better since I replaced j by j minus 5. So let me write this. This is f of k. And this is f of k minus p. So in this example, our index was j instead of k. But aside from that, it's the same thing. We shifted by p equals 5 so that we added 5 to each of the indices, each of these bounds on the index. So 3 and 6, we added 5, 8, and 11. But then in the function, you actually have to subtract the 5. So you replace the j by the quantity, j minus 5. So this is shifting the index. Another extremely important property is linearity. So there's linearity. And again, it's nicest to give this as an example. I'll start with k and go k equals 5 to 8 of, care, 3, no, I don't need to pick integers. How about 1.7 k squared minus the square root of 3 times the sine of k? Suppose I take this sum. What is it? Well, it's, if you write it out, it's 1.7 times 5 squared minus the square root of 3 times the sine of 5, because you put in k as 5. Then you add to that what you get when k is 6. So you get 1.7 times 6 squared minus the square root of 3 times the sine of 6 plus, no, we're not going to evaluate this. We're not going to get some decimal for it. It's not where I'm going with this. 1.7 times 7 squared minus the square root of 3 times the sine of 7. And then plus 1.7 times 8 squared minus the square root of 3 times the sine of 8. Great. What are we going to do with that? Well, we're going to split off all of the 1.7 times k squared parts. So this part, this part, this part, and this part. You group those together, and you factor out the 1.7. This is 1.7 times what? 5 squared plus 6 squared plus 7 squared plus 8 squared. Okay. And what about the other parts? Well, I'm going to write a plus, which might seem a little strange, but I'm going to write a plus, and then there's all the square root of 3 sine of 5, the square root of 3 negative square root of 3, negative square root of 3, sine of 6, negative square root of 3 sine of 7, and negative square root of 3 sine of 8. I'm going to factor out the negative square root of 3, but after that I get the sine of 5 plus the sine of 6 plus the sine of 7 plus the sine of 8. What's the point? The point is this is 1.7 times this summation plus negative square root of 3 times this summation. So what we're finding, if you write everything out, what we're finding is the sum, as k goes from 5 to 8, of 1.7 k squared minus the square root of 3 times the sine of k is the same as, you can split up sums and pull out constants, or split up differences and pull out constants. This is the same as 1.7 times the sum as k equals 5 to 8 of k squared plus the negative square root of 3 times the sum as k goes from 5 to 8 of the sine of k. This is linearity. You can split up sums and differences and pull out constants. So the general statement would be if I have two functions and some constants, I take the sum as k goes from m to n of some constant times one function plus some constant times another function. I can split this up and write it as a times the sum as k goes from m to n of f sub k plus b times the sum as k goes from m to n of g sub k. Okay. Those are the most basic properties of summations. When you write out examples, they all seem kind of blatantly obvious. They follow from properties of real numbers that you've known for a long time. When you write them in summation notation, they don't look so obvious. They're not something you're so familiar with, but they do enable us to prove a lot of formulas very quickly and formally without having to write out long examples and lots of dots. So let's do an example of putting all these together that's not so trivial. So just doing some algebra, some manipulations with series using these properties. So there's an example. I want this one. So an example. Let's look at 2 times. The sum as k goes from 3 to 50. So we don't want to write out this sum, definitely not, of k times k minus 1, and then subtract the sum as k goes from 1 to 50 of k plus 1 times k plus 2. So this. What do we want to do with this? Well, I'm going to say simplify. Of course, what's more simple in one person's mind isn't necessarily more simple in another's, but really we want to just practice manipulating these things using our basic properties. So there are at least two ways we could simplify this, that it would look better. We'd like to combine the summations, but we can't do that. You might think, well, we can use linearity and just move this 2 inside here and then combine the summations and move the minus sign in. We can almost do that, except the indices of the summations, or the range of the index. The index here goes from 3 to 50. The index here goes from 1 to 50. So we can't quite do that. Now there's one easy thing we can do, and there's one more complicated thing we can do. So why don't we take a look at both of them? So let's move the 2 inside here and the minus sign inside there. So we get the sum is k. So this is linearity. That linearity says you can pull out constants, but we're going the other direction. It also says you can move them inside. So this is this. And then there's, I'll write a plus. The sum is k goes from 1 to 50 of negative. So I'm moving the minus sign inside too. This. We'd like to continue using linearity and go, oh yeah, and a sum of sums, we can just write one big sum. But the indices don't match the range of the index. This one goes from 3 to 50. But we can split off 2 of these, right? We can split summations. This is, the sum is k equals 3 to 50 of 2k times k minus 1. And now just use that you can split sums. This is the sum of, I'm going to write the one we want first, k equals 3 to 50 of minus k plus 1 times k plus 2. But I left off part of the sum. I left off the part where k was going from 1 to 2. I picked it up at 3. So by splitting of summations, we still need the sum is k goes from 1 to 2 of minus k plus 1 times k plus 2. Okay, but now these are equal. I just split up this sum. I went first from 1 to 2, and then I went from 3 to 50. So these are equal. And now these have the same summations in the front of them, the same index, the same range on the index. They both go from 3 to 50. Now linearity says that this sum of sums is just, you can write it as the summation of this and this. So what we get is that summation we started with is actually the sum as k goes from 3 to 50 of 2k times k minus 1 minus k plus 1 times k plus 2, that 2k times minus k plus 1, right? And then plus this leftover part, but we can just plug, there are so few numbers here, we can just plug in k equals 1 and k equals 2. When k equals 1, we get a negative 2 times 3, and you add to that what you get when, so I'll write it like this, and then you add to that what you get when k is 2, which is a negative 3 times 4. And now you can simplify this stuff in the square brackets, the terms in the summation. You can just do algebra like you're used to. You get, this is 2k squared minus 2k. And then when you multiply this out, you get minus a k squared. And then you get the cross terms. There's a k and a 2k, so 3k, but it's subtracted, so minus 3k. And then plus 2, but it's subtracted, so minus 2. And then plus, this is a minus 6. And that's a minus 12. So we're going to have minus 18. Just kind of hanging out. So that's separate from this. It's not part of the summation. So one way of simplifying what we started with is to say it's the sum as k goes from 3 to 50 of 2k squared minus k squared, that's a k squared, a minus 2k minus 3k, a minus 5k, and then there's minus 2. And you do that summation, and you still subtract 18. So that's one version of simplifying this. Maybe it looks worse to you, so maybe not simplifying, but it's some practice with manipulating summations. Okay, I'm going to do a more complicated simplification. I don't know if it will look more simple or not, so I'll just say a more complicated manipulation that you could do. It's better practice with the properties, but it's significantly more work than this. So what if we shifted this in the first place so that instead of this starting at k equals 1, it started at k equals 3. So how do you do that? Well, as we said, you can just add 2 to each of these indices, but then you have to subtract 2 from the k, each of the places it appears in the terms. So that was the shifting of index thing. So shifting of indices tells us that this equals, so this first part I'm not changing right now, but the shifting of indices tells us that, oh yes, you can add 2 to each of these, the upper and lower bounds on your summation. So I can make this 3 and 52, but I have to replace the k by k minus the 2. Right? I add 2 to each of the indices, each of these bounds, but I subtract 2 from the k, so I replace k by k minus 2 plus 1, and I replace the k by k minus 2 minus 2 plus 2. So what does that give you? It gives you 2, and the sum is k goes from 3 to 50 of k times k minus 1. And now this part is minus the sum as k goes from 3 to 52 of, well now this is k minus 1, and this is k, oh. So the terms in our summation, k times k minus 1, are the same. The order is different, but multiplication is commutative. So that's the same as k times k minus 1. But now we've got the range of our summations different. Yeah, they both start at 3. This one ends at 50. This one ends at 52. So like we did in our other simplification, you split off the non-matching terms. We'll split off what happens at 51 and 52, and then have the sum as k goes from 3 to 50, and then combine it with this part. So what we can do is say that this is the same as So what we can do is say that this is the same as, so we get 2, the first part doesn't change. The sum is k goes from 3 to 50 of k times k minus 1. And then we have minus, but now I'm going to split the summation that we had. I'm going to go k equals 3 to 50 of, and I'm going to write the terms in the same order that I have them there. But that summation before split, but it was subtracted, so I still have to pick up the part that I'm leaving off, which was the part from at 51 and 52. So I still have to subtract this part. Okay, so what? Now you use linearity. You pull this 2 in, you pull the minus sign in, you combine the sums, and you get, this is the sum as k goes from 3 to 50 of 2k times k minus 1 minus k times k minus 1. And then minus, so that's all one big quantity. And then minus, you go ahead and plug in 51 and 52. So minus 51 times 50 and minus 52 times 51. So what do you get? Well, 2 times k minus 1 minus k times k minus 1. You're left with 1 times k times k minus 1. So you get this, and then minus these other two leftover pieces. So this is another way of manipulating the summations that we started with, whether you think it's more simple or not. That's another way of writing the answer. Of course, it has to equal what we got before. And it would be a good exercise for you to somehow take our final results and see how they match up. But we know they're equal because it's math. We did it 2 different ways. We have to get the same thing. So that's practice with manipulating summations. There's some corresponding difference operations, and we need to look at those briefly. So we have this notation for summations. What about differences? So we want to write things like, so this will be differences, and then we want to combine the two, sums and differences. Differences, these are frequently called finite differences in the literature, so in books, finite differences. So again, you've got a function that depends on integers. So I'm thinking of putting in different integers for k here. You just write a delta. And it means take what you get at k and subtract what you get when you take k as 1 less. So it means this. You take that expression with k in it, you subtract what you get when you replace every occurrence of k by the quantity k minus 1. So for instance, delta of k squared would be k squared minus k squared minus 2k plus 1, and that's 2k minus 1. Right? More generally, if f is a function, a real valued function, so it's what you get out of f, real numbers, is a function whose domain is the integer interval m dot dot n, then delta f is a function with domain m plus 1 to n, defined by, so the function, defined by delta f of k equals f of k minus f of k minus 1. So this is why there's this shift in its domain, because if you put in k is m plus 1, then you subtract f sub k minus 1. Well, if k is m plus 1, this is f of m, which is m is in the domain of f. But if we put in an m for k, it would be f of m minus f sub m minus 1. And we're not assuming f is defined at m minus 1. I should say that if m is negative infinity, so we mean all the integers less than or equal to n, then we're thinking of negative infinity plus 1 as still being negative infinity, so that the domain of the new function would also be all the integers less than or equal to n. It's rare that one writes this so explicitly in this form. This is the kind of thing you do. You write your function, your original function f of k is k squared, and then you just write delta k squared. So this is how you typically specify formulas. Instead of putting the function, giving the function a name, putting it in parentheses and putting a k there. And it's also true that it's still kind of standard in this to subscript by the variable, so that instead of writing f of k, just like with summations, we might write delta f sub k, and then that's f of k sub k minus f sub k minus 1. It's just notational. It's just standard or common when dealing with integer indices that you subscript by them. So integer values in the functions that subscript by them. So delta, this delta operation, this finite difference operation, is also has a number of basic properties, but delta is linear is the main one we want to worry about right now. So it's just as easy as it was to show that summations are linear. It just follows from basic algebra properties that you've known for a long time. It's that if you take delta of a constant times one function plus a constant times another function, you can split up the sums and pull out the constants. So this is a times delta fk plus b times delta gk. This is easy to show. So what are we saying? We're saying that delta of the square root of 3 times k squared plus 7 times the sine of k. What is it? By definition, this is the square root of 3k squared plus 7 sine of k. You subtract what you get when you replace the k's by k minus 1s. So you'd subtract the square root of 3 times k minus 1 squared, and you'd subtract 7 times the sine of k minus 1. But then you group these two terms together, the square root of 3k squared minus the square root of 3k minus 1 squared, and you pull out the square root of 3, so you factor it out, and you get this. And you group these two terms together, and you factor out the 7, the sine of k minus the sine of k minus 1. And yes, this is the square root of 3 times delta k squared plus 7 times delta of sine of k. So yeah, that's what this says. You can split up sums, split up this sum, and pull out the constants. Okay, that's linearity of the difference operator. One of the main reasons we care about differences is how they work with summations. This is another, like the properties of summations and differences, this is an extremely simple property, and yet it leads to interesting results. So, telescoping. Telescoping sums. You may wonder why this is called telescoping. I will explain that. So, what happens if you combine taking finite differences with taking summations? So let's take the sum as k goes from m plus 1, or m plus 1 to n of delta of f sub k. Now, I could do this with an example, but it's easy to write out the general, what happens generally, as long as you're okay with some dots in the. So you start at k equals m plus 1. So you have and so you put in k as n plus 1. You get delta of f sub n plus 1. And then you add to that what you get when k is n plus 2. And you add to that what you get when k is n plus 3. And you keep going. So there's the dot, dot, dots. You keep going. And then the next to last term would be when k is n minus 1. So I'll write delta of f sub n minus 1. And plus what happens when k is, what you get when k is n. So you get this. But what do these deltas mean? Each delta means you take this f sub whatever, and subtract f of one lower index. So this first thing, this first term, is f sub m plus 1 minus f sub m. This second thing is f sub m plus 2 minus f sub m plus 1. This third thing is f sub m plus 3 minus f sub m plus 2. Then you have all these dots. And then you get f sub n minus 1 minus f sub n minus 2, and plus the last term, f sub n minus f sub n minus 1. Okay, what happens? Why is this nice? Well, it's nice because here's f sub n plus 1. Here's minus f sub n plus 1. Here's f sub n plus 2. Here's minus f sub n plus 2. Going down to the other end, here's f sub n minus 1 subtracted, but here's f sub n minus 1 added. So all of these terms cancel out in pairs. You get everything appears with a plus sign and a minus sign. Everything appears in pairs, but one's with a plus, one's with a minus, except the very first term, or this term, actually, I'm not sure, call it the first term, but this lowest index term, so minus f sub m, and this biggest term, the highest index term, f sub n. Those are the only two that don't pair up because there's nothing below this to add it, and there's nothing above this to subtract it. But what did we just see that this equals? Everything else cancels out, and so you're left with this sum collapses to just the f sub n, that final one, minus this one, minus f sub m. And this is the general formula, that this sum, as k goes from m plus 1 to n of delta of f sub k, equals just f sub n minus f sub m, this. The reason this is called telescoping, the classical handheld telescopes, they collapsed. They collapsed and extended. They were kind of concentric cylinders, and they would have this long telescope, and it collapses to this small thing that you can carry around. Well, that's what this does. All these middle terms collapse, and you just are left with the first piece and the last piece. Okay, we're going to use that in a minute to get something more interesting, but we need some basic formulas involving differences. So let me do these quickly. And then we'll use these to derive some that don't look so basic. And then we'll combine that with telescoping to get some formulas that definitely are not basic. Okay. Delta of k. Well, that's easy. It's k minus 1. So it's 1. All right. That was easy. We already did delta of k squared, but let me do it again. Well, no, I won't do it again. It's 2k minus 1. Delta k cubed. All right. Now it gets a little complicated. So delta k cubed, that is k cubed minus k minus 1 quantity cubed. This would require you to know how to cube things or to multiply it out. I know how to cube things. You can multiply it out, but you get k cubed minus 3k squared plus 3k minus 1. And then when you subtract, the k cubes cancel out, and it negates these other signs. So we get a 3k squared minus 3k plus 1. All right. So these are easy to calculate. I mean, I'm not suggesting that you memorize them, but they're easy to calculate. You can do them very quickly, well, provided you know how to cube k minus 1. Okay, but if we combine these with linearity of the delta operator, we get some more interesting things. So what I want is, yeah, we found delta of k, and delta of k squared, and delta of k cubed. Oh, I'd like one more. Sorry, let's do one more easy one. Let's do delta of b to the k plus 1. So b is a constant. So what do you get? You get b raised to the k plus 1 minus, you replace k by the quantity k minus 1. So you just get b to the k. But then you can factor out the b to the k and get, if you factor out a b to the k, you get b to the k times b minus 1. Okay, that's an easy one too. Still, it's important. All right, now let's use linearity and get kind of formulas that aren't as obvious or aren't as easy, but they're not hard to get. So yeah, we found delta of k squared, delta k cubed, and delta of b plus, delta of b raised to the k plus 1. But what if I wanted something so that delta of it equals k? And I want something so that delta of it equals k squared, and I want something so that delta of it equals b to the k. Well, then you manipulate these. So for instance, we take a look at this, that delta of k squared equals 2k minus 1. But we get clever, and we write minus 1 as, well, 1 is delta of k. So I write this as minus delta of k. Why would I do that? Because I want to find something so that delta of it equals k. Now I use linearity. I add delta k to, well, not yet, I don't. Add delta k to both sides, take half of it, and what I get is that k is 1/2 of delta of k squared plus delta of k. But delta is linear. This sum is delta of k squared plus k. And then multiplied by 1/2, I can move the 1/2 inside. And so what I get is that delta of k squared plus k over 2 is k. So this is a formula that, yeah, again, it's not really worth memorizing, but it's easy to derive. What we just found, and you can factor that numerator if you want, is that k equals delta of what? K times k plus 1 over 2. Okay. You can do this for k squared, but it gets a little uglier. But maybe I'll start it and not finish it. But can we find a function so that delta of it is k squared? The answer is yes. It's not terribly attractive, but it's not difficult. What do? We have delta of k cubed. And we know that that is 3k squared minus 3k plus 1. Right? Delta of k cubed, 3k squared minus 3k plus 1. We'd like to solve for k squared, but we'd like for everything else to be a delta. Well, we know 1 is delta of k. We just solve for k in kind of as a delta of something. So we're going to write this side as, oh, all right, it's 3k squared. It's 3k squared minus 3k, but we just found that k is delta of k times k plus 1 over 2. So I'm replacing the k by what we just found for it, delta of k times k plus 1 over 2. And I'll replace the plus 1 by a delta k. Now you solve for k squared. You get k squared is, you'll have to divide by this 3. You get k squared is 1/3 of delta of k cubed, that's this. You'd have to add this to both sides, plus 3 times delta of k times k plus 1 over 2. And then you'd be subtracting this term, so minus delta of k. But now you use that delta is linear. You can move the 3 inside, combine all the deltas, move this 3 inside. You get that it is delta of, all right, I'll write 1/3, and then there's the k cubed. There's the k cubed. I've got the 1/3 outside here, otherwise we'd cancel it with this 3, but plus a 3k times k plus 1 over 2, and then a minus k. So here's a function whose delta is k squared. We could simplify this. You can get a common denominator of 2 here. So just make this 2k cubed and make this minus 2k, and then it's all over 2, and so then all of this would be over 6. But it's kind of unimportant how this simplifies. It does simplify fairly nicely, but I'll let you look at that in the book. But yeah, the point is we can do this. We can find something without too much effort so that delta of it is k squared. Why do we care? Because now we can combine this with telescoping and get summation formulas that are very not easy. I wouldn't say they're difficult, but they're definitely not easy. So, for instance, so combine with telescoping. So, for instance, what is the sum as n goes, I'll say k, as k goes from 1 to n of k? Well, this is the sum as k goes from 1 to n. We wrote k as delta of k times k plus 1 over 2. And telescoping says that if you do this sum and then do of the delta, that you get what you get if you just plug n into this expression and plug in k equals 1 less than this into the expression. So you get what you get when you put in k is n, and you subtract what you get when k is 1 less than this. I started at 1, so I put in k is 0. Oh, but then this is 0. So we just get that the sum as k goes from 1 to n of k is n times n plus 1 over 2. You might wonder, okay, is that really right? Or, as a quick example, we're getting, for instance, that the sum as k goes from 1 to 3 of k is, we should get 3 times 4 over 2. So, well, this is 6. What's this? You put in k as 1, then you put in k as 2, then you put in k as 3, and you add 1 plus 2 plus 3. Yes, 1 plus 2 plus 3 is 6. 3 times 4 over 2 is 6. Yes, we verified this for n equals 3, but we know it's true for all n. This tells you the sum of k squared. For the same reason, this will give you a formula for the sum of k squared. So the sum as k goes from 1 to n of k squared. You replace the k squared by delta of this. And what does this equal? It's really not that important that you memorize it. But what do you get? You get this expression with n in place of k minus what you get when you replace k by 0. But when k is 0, this is 0. So again, you just put n in for k. This is not the nicest way to write this. It would be nicer to factor out some terms, but I'll just go ahead and write it like this. 2n cubed plus 3 times n plus 1 minus 2n all over 6. So maybe I should factor this to make sure I didn't make any any trivial algebra mistakes, because I know how it's supposed to factor. So why don't we go ahead and do this, just so you can see it in its nice form. You can factor out a k every place, so you get a k. And then after you factor out a k, I think I'll do it up here. After you factor out a k, you have 2k squared. I factor out a k, so then I've got 3k plus 3. And then I've got minus 2k. So minus 2k, so you'd end up with just a k here. So we get this in the numerator. Does this factor? It better. It's supposed to factor as k. Well, that's that k. 2k plus 1 times k plus 1. Right? Because you get the 2k squared from this times this. The cross terms, you get a k plus a 2k. So we should get a 3k. What did I just do? Well, this is why we were checking this. K cubed, 2k cubed, 3k cubed over 3k times k plus 1 minus 2k, a 3k, k. Oh, I factored out a k, and then I put it back in over here. So you get a k times 2k squared plus 3 times k plus 1, so plus 3k plus 3. Right? We're getting see, I should have done this in more steps. We factored out a k. We're left with a 3k plus 3, and then you subtract. I factored out this k, so minus a 2. That looks a little better. So this is k times 2k squared plus 3k plus 3. So that's plus 1. And now, yes, I'm very happy. This is k times 2k plus 1 times k plus 1. Yippee. So you get the 2k squared. You get a k plus 2k, so a 3k plus 1. Yes. Yes, that's what I get for skipping steps. 2k plus 1 times k plus 1. And up here, you could write this most nicely in that form. N over 2n plus 1 times n plus 1. Okay. So you get that non-trivial formula. And then there's one last formula that we'd like to get. It comes from this one. What's something whose delta is b to the k? Well, we can just divide both sides of this by b minus 1. And you get 1 over b minus 1 times delta b to the k plus 1 equals b to the k. Well, to do that, we need b is unequal to 1. So b unequal to 1. And then this is a constant, so you can just move it in here. So delta of 1 over b to the k plus 1 over b minus 1 is b to the k. So what's the sum as k goes? I'm going to start at 0 now, from 0 to n of b to the k. All right, because I don't want to have 0 to the 0, I'm now going to also say b is also unequal to 0. But aside from that, well, this is the same as, that looks like unequal to. This is the same as the sum as k goes from 0 to n of delta of b to the k plus 1 over b minus 1. But then you use telescoping. This telescopes. And what do you get? You get what you get when you plug in n for k minus what you get when you plug in k is 1 less than this. So when k is minus 1. So you plug in b is n, and you get b to the n plus 1 over b minus 1, minus what you get when k is negative 1. When k is -1, we would get b to the 0, that's 1, over b minus 1. They have the same denominator, so you get b to the n plus 1 minus 1 over b minus 1. So these are the fundamental properties of adding, of taking summations and taking finite differences, telescoping sums. There were some very special sums. We will use these later, that the sum of b to the k, as k goes from 0 to n, is this expression. We'll use in examples that the sum of k squared is given by this formula, and that the sum of k is given by a formula that I think is gone from the board. The sum of k, just k, is n times n plus 1 over 2. These are basic properties. We care about them in a more physical context. We're trying to get at the notion of continuous summations. This is just terminology, some basic results, and some notation that'll help us a lot later.